Today's lecture is based on similarity based technique for image segmentation. So what is image segmentation? Group similar components to obtain a compact representation. This grouping can be based on pixels in an image frames in an videos. So applications finding tumors, veins, etc. in a medical images, finding targets in a satellite or aerial images, finding people in a surveillance images, and summarizing videos. So methods are thresholding, K means clustering, etc. So in the previous video, we had already discussed about discontinuities based image segmentation. So in this lecture, we are going to discuss about similarity based image segmentation. The principal approach in this category are based on thresholding, region growing, region splitting and merging. Now what is thresholding? Thresholding is one of the simplest method for image segmentation. One way to extract the object from the background is to select a threshold capital T that separates object from the background. So if at any point x comma y for which f of x comma y is greater than t is called object point, otherwise the point are called background point. So the segmented output image g of x comma y is equal to 1 if f of x comma y is greater than t, or 0 if f of x comma y is less than or equal to capital T, where t is a constant applicable over the entire image. Then the above process is called global thresholding. So you can see in this figure that this is an histogram of an image where all the pixel values whose intensity value is greater than t belongs to an object, and all those pixels whose intensity value is less than t belongs to a background. So image with dark background and a light object. So if we are going to select an appropriate t, which is the valley point of these two clustering of intensities, then we are going to get a segmented output image. So these segmented output image segmentation depends upon the selection of an appropriate threshold value. You can see in this figure that object intensity values are clustering towards the lower intensity values, and the background pixel have an intensity values are clustered towards the high intensity value. So if we are going to select an threshold T here, for example 127, if you are going to select a T, then all those intensity values, pixels whose intensity values are greater than 127 are grouped together, and all those pixels whose intensity values are less than 127 are grouped together. So we will get a segmented output image. Now the selection of an appropriate threshold is very important. For example, this is an original input image, and this one is a corresponding histogram. So if we are going to select a threshold value 50, then we are going to get an output image as shown in this figure, where though there is a proper segmentation, where background is separated from the object, while if we are going to select a threshold value which is more or less near to this clustering of pixel intensity values, then we can get an output here. So if you are selecting a threshold value 75, you can find that there are some kind of errors. Even if we are going to select an threshold value too low, then there is a error in the figure. So this output figure is this output image is not clearly segmented. So selection of an appropriate threshold values plays an important role in image segmentation. Now if we are going to select a too low threshold value, then we can see in this figure there is a loss of information. And if we are selecting too high, then even though we do not get an appropriate segmented output. So selection of appropriate threshold values plays an important role for image segmentation. Now there is a method of selecting an appropriate threshold value, which is known as automatic global thresholding. So when the intensity distribution of an object and background pixels are sufficiently distinct, it is possible to use a global threshold applicable over the entire image. In most applications, there is usually enough variability between the images that even if global thresholding is a suitable approach. So, so select an initial estimate for T that is decided by an user. So segment the image using that particular T. That will produce two set of groups. So one is known as G1, another one is G2. So G1 will group all those pixels whose intensity value is greater than T, and G2 will group all those pixels whose intensity value is less than or equal to T. Now we are going to take an average of gray level intensity of G1 and G2, which is represented by mu1 and mu2. In the next step, we are going to select a new threshold value, capital T, which is a mean of mu1 and mu2. Now repeat this second step to fourth step until we get a value of T is smaller than the predefined value parameter, that is delta T. Now this is an example of global thresholding based on iteration. So figure A shows the noisy fingerprint and figure B shows the corresponding histogram. So if we can clearly see the deep valley here, we can choose a threshold value that is an average intensity value of this one. So if T is equal to, for example, 127, then we are going to choose delta T is equal to 0, and after third iteration we are going to get a suitable value of T, which is 125. So it works well in a situation where there is a reasonably clear valley between the modes of histogram related to objects and background. Delta T is used to control the number of iterations. Initial threshold must be chosen greater than the minimum and less than the maximum intensity level in the image. The average intensity of image is a good initial choice for capital T. Now, role of noise in an image thresholding. As you can see in this figure A, that it is free of noise, and this figure D is corresponding histogram that consists two spikes. Segmenting this image into two regions is a trivial task. We just select a threshold anywhere between these two modes that will segment the image. Now figure B shows the original image corrupted by a Gaussian noise of mean 0 and a standard deviation of 10 intensity values. The modes, this is corresponding histograms, the modes are broader now, but there is a separation is enough so that depth of the value between them is sufficient to make the modes easy to separate. A threshold placed between these two peaks would do the job, will create a segmented output. While in the figure 3, the figure 3 is corrupted with a Gaussian noise of mean 0 and standard deviation of 50 intensity values. So this is corresponding histogram, as there is no way to differentiate between the two modes without additional processing. So it will be very difficult to segment this image. So non-uniform illumination may change the histogram in the way that it becomes impossible to segment the image using a single global threshold. Choosing a local threshold value may help us. Now, role of illumination in image thresholding. As figure A illustrates a noisy image, which we in the previous figure we have taken the same image that is shown in figure B. So that corresponding histogram, so you can clearly see there is a depth, so we can select an threshold value here, and that will segment an image. Now if we are considering a non-uniform intensity such as intensity RAM as shown in the figure, whose histogram is shown in this figure E, and now we are going to multiply this figure A into figures B. Finally we are going to get a figure C, which is a multiplication of figure A and figure B, and the corresponding histogram is shown in figure F. So now you can see there is no clear depth of value. So we cannot choose a single global threshold value that will segment this output image. So we need some kind of additional processing to segment this image. So we have to move towards a adaptive thresholding. So in this we are going to, so if we are choosing a global thresholding value, then you can see the output response or the segmented response of this image, and that is a very poor segmentation. So the solution is, if we are going to divide our image into n number of sub images and choose a local threshold for each image, then that will give a better result as compared to this figure, as compared to global thresholding. You can see if we are going to choose a local threshold for each image, then there is an error only in these two sub images. So that gives a better segmented output as compared to a global thresholding. So in the case of adaptive thresholding, subdivide original image into a smaller areas, utilize a different threshold to segment each sub-images. Since the threshold used for each pixel depends upon the location of the pixel in terms of the sub-images, this type of thresholding is a adaptive thresholding. So now we can classify thresholding into three types. If the threshold T is only depends upon the intensity value of that particular pixel, then it is called global thresholding. If it depends upon the intensity value of that particular pixel as well as the neighbor pixel's intensity value, then it is called local. And if it depends upon the neighbor pixel intensity values, location of the pixels and intensity of the pixel, then it is called dynamic or adaptive thresholding. Now in all these thresholding, whether it is a global thresholding or adaptive thresholding that we had discussed so far, none of these cares about the accuracy of the thresholding or how accurate or what is the error that has been involved by using these thresholding process. So we can go for a kind of thresholding by making use some statistical properties of the image where the mean error of the thresholding operation will be minimum. So optimal global and adaptive thresholding. This method treats pixel value as a probability density function. The goal of this method is to minimize the probability of misclassifying pixel as either object or background. There are two kinds of error: mislabeling an object pixel as a background and mislabeling a background pixel as an object. So you can see in this figure, if we are going to select a T here, so all those, so greater than T, all those pixels whose intensity value is greater than T are going to be grouped together and represented background, and all those pixels whose intensity is less than T are going to be grouped together and representing the object. So in that case, all those pixel whose intensity value is greater than t, but they belongs to an object are now misclassifying as background. Similarly, all those pixels whose intensity value is less than t belongs to a background, but now they are classifying as an object. That will lead to an error in segmentation. So method for estimating threshold that produce the minimum average segmentation error. Let an image contains only two principal gray region and Z represent the gray level values. These can be viewed as a random quantities and the histogram may be considered an estimate of their probability density function Pz. So normalized histogram can be viewed as probability density function of this random variable Z. So the normalized, now we assume that the image contains two major intensity regions to dominate the intensity values. So our histogram will look like a bimodal histogram. Now P1Z indicates the probability distribution function, the probability density function of the intensities of pixel which belongs to say background, and P2Z is the probability density function of the pixel intensity values which belongs to an object. And this overall histogram, that is Pz, now can be represented as a combination of P1Z and P2Z. So overall Pz can be write as capital P1 into P1Z plus capital P2 into P2Z, where P1 is the probability that a random pixel with value Z in an object pixel, and P2 is a probability that a random pixel is a background, and P1 plus P2 is equal to 1. Now this blue color indicates P2Z and red color represent P1Z, and this green color indicates the overall probability density function, that is Pz. So in this particular case, if we choose a threshold T somewhere here, and I can say that if f of x comma y is greater than t, then x comma y belongs to an object. Now here you find that though we are taking a hard decision that f of x comma y is greater than t, then x comma y belongs to an object, but the pixel with intensity values f of x comma y is greater has also a finite probability that it belongs to a background, as you can see in this red curve. So while taking this decision, we are incorporating some error. This error in the area given by the probability curve for the region intensity value greater than t. Now the probability of considering a background point as an object leads to an error even t, because this error is a threshold dependent. So even is a function of capital T. So even t is equal to P2 Z dz. That will integrate from minus infinite to capital T. That is a background error, that background pixel that are going to be considered as object. Similarly, there is an error E2, the object pixels that are going to be considered as background. So E2t is equal to minus infinite to t P1 Z dz. Now the overall error capital E is P2 even t plus P1 E2t. Now we want to minimize that error. So we are going to differentiate that error with respect to threshold. So d of e divided, so there is a derivative of error with respect to threshold, which is equal to this. And now we have to minimize it. So we are going to equate it to 0. So in that case, P1, capital P1 into P1T is equal to capital P2, P2T. So if P1 is equal to P2, then the optimum threshold is where the curve P1Z and P2Z intersects. This one. So now we are going to try to solve this problem. So for that we must know P1 and P2. So we are considering Gaussian probability density function. So P1Z is equal to 1 upon sigma 1 under root of 2 pi e to the power minus in bracket z minus mu1 square divided by twice of sigma 1 square. Similarly, we are going to consider P2 also a Gaussian probability density function, where mu1 and sigma 1 square are the mean and variance of the Gaussian distribution density of one object, and mu2 and sigma 2 square are the mean and variance of the Gaussian density of the other object. So now as we know, Pz is equal to P1 into capital P1 into P1Z plus capital P2 into P2Z. So now Pz is equal to P1 upon sigma 1 under root of twice of pi e to the power minus times T minus mu1 square by twice of sigma 1 square plus P2 upon sigma 2 under root of twice of pi e to the power minus T minus mu2 square divided by twice of sigma square. So now if you want to solve this equation, we are going to take the log of this one and simplify this equation as a quadratic equation. So at square plus bt plus c is equal to 0, where a is equal to sigma 1 square minus sigma 2 square and b is equal to twice in bracket mu1 sigma 2 square minus mu2 sigma 1 square, and c is equal to sigma 1 square mu2 square minus sigma 2 square mu1 square plus twice sigma 1 square twice sigma 2 square ln sigma 2 P1 divided by sigma 1 P2. So here it has been written as O while it is sigma 2. So now capital T is equal to mu1 plus mu2 divided by 2 plus sigma square divided by mu1 minus mu2 ln P2 by P1. If P1 is equal to P2 and sigma is equal to 0, then the optimal threshold is the average of the means, or T is equal to mu1 plus mu2 divided by 2. So this is an example. If this is as a original image of polystyrene cells taken by the optical microscope, and this one is corresponding histogram, and if we are going to select a global threshold value, then figure C shows the corresponding segmented output image, while the figure D shows if we are going to use an OS2 method, OS2 thresholding method, which is also known as adaptive thresholding method. So this gives a better result as compared to basic global thresholding. So there is another option, that there is another method, that is multi-level thresholding. Now there is another kind of thresholding that is known as multi-level thresholding, or you can also call it local thresholding. As you can see in this figure, there are number of deep values. So if we are going to select in this figure, for that kind of figure, we are going to select more than one thresholds. So if a point x comma y whose pixel values is less than t1, then they belongs to a background, If it is greater than T2, then that belongs to an object of class 1 or A. If it lies between T1 to T2, then they are belongs to another object B. So you can see in this figure that this one is an original object and the corresponding histogram. So if we are going to choose a single global threshold value, then the corresponding output is a poor segmentation. And if we are going to select a local thresholding, if we divide this image into number of sub images and the corresponding, we are going to select a different threshold for each images, and finally we are going to merge that one, then we get a better response, a better segmented output. So in the next lecture, we are going to discuss about local thresholding. Thank you.